Okay, finally we are here. All right. So we derived, up till this point in this course, the essential things that we wanted to do was develop the basic equations, the Navier-Stokes equation, the continuity equation that you see here, the energy balance equation, and the mass balance, species mass balance equation. What you should be able to do at this stage in this course is to recognize each one of the terms in those equations. What is the physical meaning for each one of them? For example, in all those equations on the left-hand side, you have essentially the Lagrangian derivative, the substantial derivative of whatever the quantity that is being monitored. In the first case, it's momentum. Second case, it is temperature. In the third case, it's concentration. But there is an accumulation term, which is the temporal changes with temperature or concentration or velocity. And then there is a convective term. So this second term here is called the convective term. Convective meaning that quantity that is being conserved, whether it's momentum, heat, or mass, is carried from one place to another place by the velocity itself. Okay, so that's a convective term. On the right-hand side, in every one of those equations, you have a diffusive term. Okay, that captures the molecular mechanism by which momentum is transferred, heat is transferred, or mass is transferred. And then there are extra terms appearing in each one of these equations. And those are, for example, the gravity and the pressure in the momentum equation, the heat source, the conversion of friction into heat that is captured in the energy dissipation term in the energy balance equation. And in the mass balance equation, you might have a term that converts a species from one to other. For example, if you have methane and you're burning it in oxygen to produce carbon dioxide and water, there will be a species creation term and a destruction term. And you will have, in fact, many such equations, one for each species, methane, oxygen, water, carbon dioxide, etc. Okay? And the similarity between these equations is the fact that it's a balance between convection and diffusion on the left-hand side and right-hand side. If you neglect for the moment all the other terms, then you can make them mathematically identical if you make, for example, this Prandtl number defined as ratio of momentum to thermal diffusivity as equal to 1, or the Schmidt number, which is the ratio of momentum to mass diffusivity to 1, then the equations become identical. So there is an analogy, there's a similarity between these. And in the last lecture then, towards the end, we started developing solutions. So the rest of the course is going to be about solving these sets of partial differential equations under various conditions, subject to the typical boundary conditions and initial conditions that we will see. So the first problem that we started analyzing in the last lecture is the so-called rectilinear flows. Flows in which there is only one velocity component and the other two are zero. And that particular velocity component could depend on time and two perpendicular coordinate directions. Okay? But so it can vary in the direction perpendicular to which it is pointing out. For example, if this is V1, V1 could be functions of x2 and x3 in a plane perpendicular to it, but these are also called unidirectional flows, flows that are flowing in single direction. There's no velocity component in the other direction. So given this, what you should be able to do is simplify the Navier-Stokes equation, the continuity equation, which you're doing in your current assignment as well, the second problem. And so this is essentially the simplified Navier-Stokes equation. The continuity equation you will find in all these classes of rectilinear flows is trivially satisfied. Okay? So it is automatically satisfied. So it's only this equation that you need to satisfy. And there are three momentum equations, but two of them are also trivial because V2 is 0, V3 is 0. So every term in those two components of the momentum equation will be 0, as we saw in the last class. So there's only one term that is non-zero, and we need to use that to solve the only unknown in this case, which is V1, the velocity component. And so we need to now define a geometry into which that equation applies and learn how to solve that particular equation. Okay, any questions on how you simplify these equations? This will become repetitive. We'll keep doing this for a whole variety of problems. Yeah?
What's the sub D on the dp sub d ds?
Yeah, this is coming from, can you guess where it is coming from? Gradient of P term. When you expand that in the x1 component, it will be dp1 dx, dp dx1. But I don't have any gravitational term here. Okay, so what that means is I'm interpreting the pressure as dynamic pressure. So the D stands for the fact that it is a dynamic pressure. Okay, so I'm not explicitly accounting for hydrostatic variation because that cancels with the rho G. And I wrote that not as a partial derivative but as a total derivative. And the reason is in such flows, to fix ideas, for example, if I have some arbitrary cross section, but the cross section is uniform, it's extruded, that plane is extruded, so the pipe cross section could be arbitrary. So that would be your x1 direction. These are x2 and x3. Thank you. Okay, so the flow in this case is all pointed in the x1 direction, but where does it derive its energy? How is it flowing? That is coming from an externally applied pressure gradient by a pump. Okay, so in this case we would call this as the forcing term. The flow is forced by an applied pressure gradient. Typically we will come across two types of external forces that can cause the fluid to move. One is an applied pressure gradient, the other one is a moving wall. So I could have a moving boundary and the fluid sticks to that, so that can generate a flow inside any domain. Okay, so for example, piston in a pump or centrifugal pump, the vanes, the turbines, these are all moving boundaries that cause the fluid also to move. So these are the two typical sources of external excitation that can cause the flow to be non-zero. So if that is, if dp dx is 0 in this case, then the flow has to be 0. There is no flow. Everywhere the velocity is 0. So you get a trivial equation once again. Okay, does that answer your question? So the dpd dx1 is the dynamic pressure head that is developed by a pump that is known, that is given, that drives the flow. Okay, so that equation still is a partial differential equation, but let me ask you, is it a linear or a nonlinear partial differential equation? In this one, dpd dx is given. Okay, so we're going to take that as a known quantity, but v1 is the unknown. v1 appears in all these places. But v1 doesn't have any nonlinear term. There are no products of v1 or derivative of products of v1. So that would be classified as a linear partial differential equation, which in principle can be solved analytically. Of course, we can also solve that using COMSOL very easily. Okay? But we are going to simplify the problem even further. We don't want to begin solving PDEs directly. Okay? So we're going to make another assumption that the flow is steady. So if the flow is steady, that means that there is no variation with time. Okay? And we're going to assume that the flow is flowing between two parallel, infinitely long plates, and it is fully developed and it is steady. Okay? So when I make that assumption, this condition that v1 is a function of t x1, x2, x3 becomes v is a function only of x2. So I can simplify further, dropping terms that do not depend. v1 does not depend on t, so I drop the left side, and v1 does not depend on x3, so I drop this one. But what is the geometry I'm considering? The geometry I'm considering is flow between two parallel plates. Okay, so this is the geometry. So perpendicular to the board, I have to think of it as being infinitely long. Perpendicular to the board, it's infinitely long. So it is an idealization. Why do we make this idealization? We want to go through the process of how do we solve it and what can we get out of it, okay, by solving this problem. So we have two infinitely long parallel plates, and as we saw in the last class, the flow will be two-dimensional in the entrance region. This is called the entrance region up to this point. Okay, but we are interested only in the fully developed region where the velocity is only depending on the y direction. So if I call this as x and I call that as y, okay, so I have basically vx, which is a function of y. That is all I have. It does not depend on z. Why does it not depend on z? Because it's infinitely long. So no matter where I take the plane, if I take a cut here or a cut there or a cut there, I will get the same velocity profile. There is no reason for it to change. Okay? This is not in reality true. We will see what kind of behavior fluids can exhibit, but it's certainly true under very low flow conditions. Okay? So we are saying that there is no variation in the z direction and there is no variation in the x direction itself. So if I take a snapshot here or a snapshot there, I'm going to get exactly the same profile. That reduces the equation to an ordinary differential equation because, as you saw, we have dropped this term and we have dropped this term. So basically, I have only d square v1 dx2 square, or y square in this case. So I'm treating x1 equals x, x2 equals y. This index notation to the normal Cartesian or cylindrical, you should be able to keep track of. Okay, so that equation simplifies to the following. This is the Navier-Stokes equation for a 1D flow between two infinitely long parallel plates at a finite distance from each other. Okay. So now I need to specify a set of boundary conditions. I need to isolate the system from the surroundings, and my domain is going from the bottom plate to the top plate. Okay. So here I guess I have labeled the bottom one as 0 and the top one as 2b. Okay, so this is 0, this is b, and this is 2b. That is, the gap between the two plates is 2b. Okay, and that is the x2 direction or y direction. And this is the equation of motion. And in here, I have moved mu to the right hand side, and I've called this entire thing 1 over mu dp dp d dx1 as a constant because it's a pressure driven flow. Okay, so I know what this right hand side is. I know what the viscosity is. So it is a known constant, and that is a constant that forces the velocity to be non-zero. For example, if I set c equal to 0, that means there is no applied pressure gradient. And then I know that the velocity at the upper plate is 0, the velocity at the lower plate is 0. Okay? So what would be the solution for that case? If I have d square v1 dx2 squared equal to 0, subject to the boundary condition v1 is 0 at both the top and the bottom, what solution will satisfy that? What function of v1 will satisfy this differential equation together with these boundary conditions? Zero solution. Okay? This is called a homogeneous equation with a homogeneous boundary condition. So immediately you can, by looking at it, you can say homogeneous meaning on the right hand side is 0. So the only solution that will satisfy this is v1 equal to 0. So you need to have an inhomogeneity. You need to have a non-zero forcing term on the right hand side in order to have the velocity as non-zero. Okay, and once you have that, you should be able to integrate this twice. So I'm integrating once by separating that, you know, right? dx1 of dv1 dx1 equal to c. So separate and integrate. So it is d of dv1 dx2 equals c times dx1. And c is a constant. So you can separate that and you can integrate that. And what you will get is dv1 dx2 equals c times x2, because integral of the derivative of x2 is just x2 itself, plus an integration constant. This is an integration constant. We need to find out from the boundary condition. This is what you are doing in your current assignment. If you've done that for the second problem, you need to do very similar integration and then evaluating the boundary conditions. You integrate one more time. So v1 equals c times integral of x2, which is x2 squared over 2, plus a1 times integral of dx2, which is simply x2. Okay? And then another integration constant. Because it's a second order equation, you will have two integration constants, and those are a and b. We need to find them out by imposing the boundary condition. Any questions on that? You're comfortable with integrating these ODEs, right? Okay. Now we evaluate what these boundary conditions are by putting, what the constants are, by putting at x2 equal to 0, the velocity is 0. That gives you right away that b is equal to 0. Okay? So we found out what b is. Then at x2 equal to 2b, that is at the top plate, the velocity is again 0. Okay? So here, wherever you had x2 in this place and in this place, you substitute equal to 2b. Okay? So that becomes 4b square, and this becomes 2b, and once again you set that equal to 0 on the right hand side and solve for a, and so a becomes minus cb. And so the solution is, after you substitute for a and b, you get this expression. v1 is equal to c times x2 multiplied by x2 over 2 minus b. So that is a parabolic profile. It's a quadratic equation. So if you plot the velocity profile between those 2 points, you'll find that it's a parabola with a maximum and at the middle. And it does satisfy the 2 boundary conditions. The boundary condition is at x2 equal to 0, it is 0. At x2 equal to 2b, it is also 0. And it does satisfy the Navier-Stokes equation. Okay? Now, I don't know whether all of you are following the discussion that I just posted on the forum. There was a question from Chad, I guess, about when does the momentum flux peak, or when does it become 0? Okay, so in this case, you can notice that at the center point, the velocity gradient is 0. Okay, so if the velocity gradient is 0, what can you say about the diffusive flux? What is diffusive flux? The shear stress. Okay, what can you say about the shear stress at the middle point? 0, because it depends on the velocity gradients. So whenever you have a local maxima or minima in the velocity profile, at that point, it will be a point where the shear stress is equal to 0. Okay, because shear stress depends on all the velocity gradients. So once you have the velocity profile, you can answer. Now you can start analyzing the problem. You can answer questions like, what is the shear stress at the wall? What is the force? Like what force do you need to apply to the wall to keep it from not moving? For example, if the fluid is moving, if the plates are free to move, it will be dragged. Okay, so you need to apply a force to the plate to keep it from moving. So what is that force? You can answer questions like that. And then what is the flow rate for a given pressure drop? Because pressure drop is what you know. So you know from the pump capacity what is dP dx that you are applying. Okay? So for that pressure drop for a given fluid, whether it is syrup or whether it is water, if you want to answer the question, how much of fluid can I pump? What is the flow rate? You can answer that question also by integrating the velocity field to get the total flow rate. Okay. So what is the flow rate? The flow rate is determined from an equation like this. Q equals integral of v1 dx2, integral from 0 to 2b. Now, when I write something like this, if it is not clear, you have to stop me there. Okay. Are you following where that equation comes from? What I'm doing there is, this is the geometry that we are looking at. Okay. So I'm taking a differential area perpendicular to the flow. Okay, so what is flow rate? Flow rate is velocity times the area. So if I have the velocity v1, and if I multiply this by dx2 times 1 in the perpendicular direction, in the z direction, I'm taking a unit length. So this is flow rate per unit width perpendicular to the board. That's what this Q is. So that is essentially velocity times the cross-sectional area. Gives you the volumetric flow rate. So that's how this v1 times dx2, then you integrate that because the velocity actually changes from point to point. So you need to find out that is a flow rate that is flowing in this section is going to be smaller than the flow rate that is flowing in the middle section. So we need to account for that and integrate that. And when you integrate from the bottom to the top, you get the total flow rate. That is a general conceptual statement that says the flow rate can be obtained as integral of v times dA. dA in this case is dx2. And then, whatever the problem that you're solving, you know the velocity profile, take that velocity profile and insert it there and carry out the actual integration. And that's what this step is. Okay, and then you integrate that between the limit 0 to 2b, and you get the integration, the constant of integration. Okay, and that can be written as minus 2 over 3 b cubed 1 over mu dp dx1. So here I have resubstituted for what C is. C is 1 over mu dp dx. So that gives me the relationship between the flow rate and the pressure drop. So if you tell me what the pressure drop is for that geometry, I can predict the flow rate. Or if you tell me I need to pump so much of flow, what should be the pressure drop, I can calculate that. So there is a unique relationship between the pressure drop and the flow rate. And interesting thing to notice is that it appears as inverse of viscosity. So the more viscous the fluid, the less flow that I can achieve for a given pressure drop. Okay? Or if you want to achieve a given flow rate, then you will take this to the left-hand side, and you'll find that the pressure drop increases linearly with the viscosity. The more viscous the fluid, the larger the pressure drop that you need. So you get a nice algebraic relationship between macroscopic quantities, pressure drop and flow rate. And the other thing that you see is, of course, the gap width plays an important role. If it is small, the flow rate obviously has to be small, but it says that it goes as and once you have the flow rate, you can find the average velocity, which is a flow rate divided by the cross-sectional area. In this case, the total cross-sectional area is 2b multiplied by 1. That unit is 1, perpendicular to the board. So the area is simply 2b. And that gives you the average velocity, if you want to calculate the average velocity. Okay, so we have analyzed the Navier-Stokes equation, simplified it, set up the boundary condition, solve that to get the velocity profile, and then we are able to get the flow rate, and we are able to get the shear stress on the wall. So if I'm interested in the shear stress on the wall, I need to decide which component of the shear stress is appropriate for this case. Okay, in this particular case, if this is x1 and that normal is x2 in the x2 direction, then I want tau 2,1, because the first index refers to the surface, which has a normal in the x2 direction. Okay, so that surface is the top plate here that you will see, okay, of the two plates, and 1 is the direction in which I want the force to be calculated. So that is given by mu plus d1 dv1 dx2. How do I know that? You just have to look it up in the appendix in your textbook. This will be given to you in an exam. Okay, but you need to make the choice that it is this I need to calculate. The table will give you all the 9 components of the stress tensor. You need to decide this is the appropriate component that I want to calculate. And in this case, of course, dv2 dx1 will be 0 because there is no v2. Okay, so dv1 dx2 you can calculate because you know how v1 changes with x2. Just go to that expression, take its derivative, okay, and then you want to evaluate it at the top wall. Where does that information go? It's here. So after you take the derivative, you substitute x2 equals 2b, that is at the top wall. Okay, and that you get the shear stress as this, mu times c times b. So that is the force that you need to apply to the top wall to keep it from moving when you are applying a pressure gradient to move the fluid from left to right. Okay, any questions?
Why is dv2 dx1 0?
Because v2 is 0 in this particular problem. We started by assuming that there is only one non-zero velocity component, which is v1. So there is no flow in the vertical direction, and there is no flow in the z direction. That is assumption. That's why it's 0. Yeah. So if I calculate, for example, tau 2, 3, what do you think would that be? 3 being the z direction perpendicular to the board. Okay, that is the x3 direction. And I'm saying calculate tau 2, 3 for me for this particular problem. What would you expect that to be? 0, right? Because there is no flow in the third direction, so there are no gradients of the velocities in the third direction, so that component must be equal to 0. Okay? Now, what does this result tell you about the nature of variation? The velocity profile was parabolic, but the shear stress profile is linear. Okay, and what is it at x equals b? x2 equals b? 0, and that's what you would expect because the velocity profile is maximum at the middle, so that plane in the middle should be the plane of zero shear. There is no shear stress on the plane. Okay. Now, a question for you to think about: is this profile valid for all flow rates? Okay, if I do the experiment, will I realize this profile at any flow rate that I choose? Now, one of the things I guess I should point out is, because for as long as you're sticking with Newtonian fluids, density and viscosity are well-known properties. Okay, this is actually a very good model. So whatever you predict from this, the velocity profile, should be realized in any experiment that you do, if we can do that experiment. Okay, in this particular case, can you do such an experiment to measure the velocity profile and verify it? If I ask you to design an experiment, would that be possible? You need two infinitely long parallel plates. Okay, that's where the challenge would be. And then you need to have a way of pumping the fluid through those two parallel plates. But one can come close to the approximation if I design, for example, a finite but very long. Okay, so I close this side and I close the other side, and the top and bottom are also closed. So it is a very thin slit, and into the slit I have some sort of a air that I can blow with a fan, for example. Okay, so I'm blowing air uniformly into the channel, and of course I need to stay away from the entrance and I need to stay away from the edges. If I measure the velocity profile right in the middle, that will agree very closely with what we predict, because as you approach the wall in this direction, you will get to zero velocity, so there will be a variation in the z direction. But in the middle of the section, there should not be any variation in the z direction. There should not be any variation in the x1 direction, which is this direction. So there will be only variation in the vertical direction, and you can predict that. Okay, and that prediction will agree with any measurement to within 0.1%. People have measured these things using fairly accurate devices like hot wire anemometer, laser Doppler anemometer, etc. Okay? So in that sense, the model is accurate and it will be valid only up to a certain flow rate. So the question that I'm asking is this profile valid for all flow rates? And the answer really is no, it is not. If I keep increasing the flow to higher and higher value, I will systematically break down all the assumptions that I have placed in this analysis. What are the assumptions that I have placed? That it is steady flow, that it is fully developed, that it is one-dimensional. Okay, so what happens is the flow becomes turbulent, and we will see what turbulence is later on. It becomes inherently time dependent, and all three velocity components will be non-zero. When that happens, we cannot solve this analytically. We have to go to the computers to be able to solve that, because the equations become highly nonlinear. Okay, but in an undergraduate fluid mechanics course, you would have answered this question for a pipe. I have a circular pipe. I will solve this pretty soon. Okay, and I have flow through that pipe, water, for example, and up to a Reynolds number of about 2100, you will find that the flow is parabolic and agrees exactly with what analysis would predict for a cylindrical geometry. But once you exceed the Reynolds number, defined as d p rho over mu, if it is greater than 2100, this is no longer valid. The parabolic profile is no longer valid. And we need to understand why that is. Towards the end of the course, we will address that issue, because it has to do with stability of the problem. Any questions? Yeah.
这个tau to 1 is minus.
Yeah, I've been sloppy throughout in the sign convention because it is a sign convention that some books will put this as a minus sign, some will put it as a plus sign. So basically it depends on, just like in work and heat, the convention is work done on the system is positive or by the system is negative. In the same way, the stress acting on the surface is positive and stress acted by the surface is negative, something like that. So ignore that for the moment. It's not going to lead you into trouble. Okay, the plus sign and the minus sign, both are used mixed in many books. You will see some books use positive, some books use negative. When it becomes important to pay attention to it, I'll point out that's why we pick the sign to be the one that we want. Okay, so a variation on in this course and in your qualifying exam, I guess that's coming in May, these are the kinds of problems you should be able to do. I mean, the simplest problem we have started will get more complicated as we go along. But variations on these is what I will expect you to be able to do on your own. Okay. Here we have studied one problem. Let's just change it slightly and see whether you can solve that. And the current assignment, in fact, is a solution in Bird Stewart and Lightfoot. It's a worked out example. You can look at it. But the assignment problem is a slight variation on that. Okay, so you should be able to take that result and follow essentially the same methodology, but focus on the question that is being asked. That is, how small should the air gap be before I cannot neglect the shear stress at the interface. Okay, so that physical interpretation, intuition, is what I'm focusing on even in lectures. When I say you can integrate that, I'm assuming that you can all integrate and substitute. So I'm not spending a lot of time actually solving for these algebraic equations and boundary conditions. I have typed them out. You can look at it. You can fill in the gaps if you want. It's the physics that you need to get and the mathematics that goes with it to be able to solve it. So a variation on the problem is, still we have two parallel plates. There is no applied pressure gradient. We already saw when there is no applied pressure gradient, there is no flow, right? Unless I move one of the plates. So now I'm going to say I'm going to move the top plate, and this is called a Couette flow. Whenever you have a pressure-driven flow, it's called the Poiseuille flow, and whenever you have a moving boundary, it's called a Couette flow. So in this case, the upper plate is moving with a certain velocity, and that velocity is given to you. U, capital U, is the velocity with which the top plate moves. Okay, and there is no applied pressure gradient, so C is equal to 0. Otherwise, it's the same geometry, so the equations are exactly the same. d square bv1 dx2 square, which is in general equals dpd dx1, but in this case it's equal to 0 because it's not the pressure that is driving the flow. Okay, so subject to two boundary conditions. What are the boundary conditions? The bottom plate is fixed. The top plate is moving with the velocity u. So those are the two boundary conditions, BC1 and BC2. Now you can easily integrate this twice because it's a trivial equation. d square v1 dx2 square equal to 0. When you integrate it once, you'll get a constant. When you integrate it twice, you'll get ax2 plus b. Okay, so that's a linear velocity profile. So if you plot the velocity profile between the top and the bottom, the top plate is moving with a velocity of u, the bottom plate is fixed. Velocity profile is going to be something like this. The velocity vectors will be something like that. It's a linear profile from the bottom to the top. At the bottom the velocity is 0, at the top the velocity is capital U, the given forced velocity. Okay, so using that you can find the two boundary conditions. So when you use the boundary condition at the bottom, it turns out that B is equal to 0. When you use the boundary condition at the top, you get A is equal to U over 2B. So the velocity profile becomes U over 2B times x2. So it is a linear profile. So if I ask you the question, what is the force needed to keep the upper plate moving? Because the upper plate moves with the velocity, but it doesn't move by itself. You need to apply a force to keep it moving, right? So what should be that force that you should apply to move the upper plate at a velocity of u? How would you answer that question? Well, I need the shear stress on the surface. So this is the normal. So I need tau 2, 1. On the surface 2, with a normal in the direction 2, and the force itself is in the direction 1. Okay, and that is going to be the same expression that we saw earlier, dv1 dx2, evaluated at the top plate. That is x2 equal to 2b. So when you take the derivative of the velocity profile with respect to 2, it's a linear profile, so the derivative is going to be a constant, right? So you get the shear stress to be constant in this case. Shear stress is the same no matter what plane you are in. And it is given by mu u over 2b. Okay, any questions on that? So this is the Couette flow between two parallel plates with a moving boundary. Let me ask you a question. How would I... This is a very important result because a variation on this is going to be our viscometer. What is a viscometer? Viscometer is a device which allows you to measure viscosity. How do you measure viscosity? For example, if you look at this expression, if I can measure the shear force, that is the shear force due to the shear stress. If I know the stress and the area on which it acts, I can find out the force. If I can measure that, and if I can measure the velocity with which that plate moves, then, and I know the gap, I designed the viscometer so that I know what the gap is. The only unknown would be mu. I can calculate that. Okay. Now the question is, how can I devise this infinitely long plate? And the answer is you cannot. But a clever variation on this would be if I take two concentric cylinders that are very close to each other, small gap. Okay. So the gap between these two, what would be the velocity profile in that gap? So imagine that the gap is much smaller than the radius of the cylinder, the radius of the inner cylinder. Okay, and if I, for example, cut the cylinder and stretch it out, what do I have? Two parallel plates, two parallel sheets, right? So it's as if I take these two parallel sheets and fold them on that so that they become a circular nature, and then I have a continuous infinitely long parallel plate that can simulate that condition because it just keeps going forever. Right? So that's a very clever design, and what you need to do is mount the outer cylinder onto a motor so that you can rotate it at a constant speed. Okay? That way you know what the velocity is, you can measure that. And the inner one is suspended on a torsion bar. A torsion bar is basically a steel wire or something that will deflect, but it will not spin. So by looking at the deflection of the inner cylinder, you can find out what is the torsion, what is the torque. You can calculate the torque. Torque is what? Force times the distance. You know the distance, so you can calculate the force, so you can figure out what the left-hand side is. You control the right-hand side, the velocity, through the motor speed, and you can measure through the torsion bar what is the torque applied on the inner cylinder. And so you can back calculate the viscosity. Okay, so this is going to be a problem in one of your assignments that is coming up later on. How to measure viscosities and what are the limitations, advantages, disadvantages, etc. on such a device. Do you understand the problem? How we are converting that result from flow between parallel plates into something that's could be used for measuring the viscosity. How many of you have seen the G.I. Taylor film, 30 minutes of it all? It won't work? Okay. Okay, from home or from here? From here. Did anybody else? Were you able to see it? You watched it. You were able to see it. Okay. There are a couple of ways we can get it. One is from the Moodle web page, I have a file directory. So if you click on that, it will go and show you all the files that you can download, the lectures in PDF format, each one of the videos in MP4 format, including those videos in MP4 format. Then you download them, and then you can watch it on your media player on your computer or take it into your cell phone or whatever. You can watch it. Okay. It may not, if you click on the direct link that I have set up, It's supposed to open up in a browser, but there are so many browsers, there are so many variations. So it'll take some time to track where the problem is, whether you're using IE or Chrome or Firefox or whatever. I don't want to get into those things, so just download it and see. If you're not absolutely able to see it, then come and see me. I can give it to you on a pen drive or something. Okay. The reason I asked at this stage is there is one part. So only one person has seen it. Nobody else has seen that. Kind of disappointed. It's a beautiful movie. It's a very, very inspirational movie. Okay, because it talks about, there is so much of wealth of knowledge in there. Every experiment is a beautiful, simple experiment that drives home a point. Okay? And one of the experiments that he shows is, I don't know whether you remember, he takes a sheet of paper and drops it on a table, right? And what is the idea that he's driving? That a thin film of fluid between the sheet that he drops and the table, there is a thin film of air, okay, that acts as a lubrication, so that the sheet will glide along the table for a very long time. But if you punch a few holes in it, the air escapes from there. Then the sheet makes contact and friction takes over and it doesn't move as much. To analyze that problem, you could use results from here because it's basically, once again, flow between two thin plates, whereas the bottom plate is the table that is fixed, the top plate is the sheet that is moving. Okay? So if you have to estimate, for example, if you know the density, the viscosity of air, if you need to estimate what would be the velocity of the sheet or how long can it go, things like that, you can get some idea, an order of magnitude estimate of the idea from the solution to this particular problem. So that is the beauty about analytical solutions, because they give you deep insight into the physics of the problem. Whereas if I set it up numerically, I'll get an answer for a specific case, but I cannot really apply it. I don't know the functional form. Here I know the functional form is, it's linear. The velocity profile is linear. The shear stress is constant. Any questions? The next case, and we are going to the rest of the course is about this. We're just going to take different examples and see how to set it up and how to solve it. Fluid mechanics, heat transfer, mass transfer with reaction, etc. We'll just keep on solving problems. So the next problem is circular Poiseuille flow. Circular meaning we are analyzing the flow in a pipe, cylindrical pipe, inside a pipe. And Poiseuille flow means it's a flow driven by pressure gradient, an applied pressure gradient. Typical problem that we encounter all the time in chemical processes. When you're pumping a fluid from one vessel to the other vessel, typically we have these cylindrical pipes. So we're going to make similar assumption, but the variation is from Cartesian frame, we are going to go into cylindrical coordinates, cylindrical reference frame. Okay? So we're going to look at the equations of motion in cylindrical reference frame, but other than that, the assumptions are exactly the same. That is, it is a fully developed flow. We are nowhere near the entrance, and so the profile is invariant in the x direction. Here, x direction is the axis, and r is the radial direction, and theta is the angular direction. So there are three fundamental coordinates that are orthogonal to each other, and axial x, radial r, and theta is the angular direction. The radius of the pipe is a. Okay, and the viscosity of the fluid is mu. So we make a postulate that the velocity in the radial direction is 0, in the angular direction is 0, but in the axial direction it's a function of only r. It varies only with the radius. So the velocity is pointed in this direction, but it changes. As you change the radius, it will change. It will be different from here to here to here to here. So the axial component of the velocity changes in the radial direction. There are no other velocity components. Okay? Is that a reasonable assumption? If you don't make that assumption, we cannot solve the Navier-Stokes equation analytically. Okay? So practical necessity, we say, okay, we're going to try that. Is it a reasonable assumption? We can only answer that question experimentally, because we can get a solution and we can say, okay, does this solution agree with what I measured? Okay, and does it agree for all Reynolds number? And the answer to that turns out to be no. It agrees up to a Reynolds number of 2100, no matter what the fluid is, no matter how big the diameter of the pipe is, okay, and no matter what the velocity is. If that combination that gives you the Reynolds number does not exceed 2100, this assumption is perfectly valid. Okay? But if it exceeds that, then that assumption fails. And that's what leads to transitional flows and turbulent flows. Any questions on the problem statement? So our goal now is to predict this velocity profile and predict this stress profile, shear stress profile, in a circular pipe. So the starting point is make a postulate for the velocity profile. So we are saying that the two components are 0, the third component is only a function of r. That's what says it's a fully developed flow. It does not depend on the axis itself. And at this stage you open up your appendix and look at what are the equations of motion in cylindrical coordinates. Okay, so in this case it is steady flow, and V theta is 0, VR is 0, Vz, the axial flow, is not a function of z. It's fully developed. Okay, so that is 0 because it is fully developed. This you should be able to do in an exam. Okay, from the statement extract these keywords, that it is fully developed, that it is one-dimensional, and assume a velocity profile for that. In some cases I might give you the velocity profile and then you start simplifying the equations. Then you look at every one of these momentum equations. Okay, you can immediately say, if I take the radial component of the momentum equation, what will it be? Yeah, z is the same as in the figure. I guess I cut and paste the figure from another place. So that should be z. Okay, the axis of the pipe is z. The figure comes from one book and the equations come from a different book. But the axis is the equations with the z direction. So it's r theta and z, or r theta and x. Okay, so if you take the r component of the momentum equation, which will be the r component of the three equations that you see there? How will you determine that? One that has r everywhere. That is the r component. So all those terms are going to be 0. But notice that there is a theta component there in that equation. So don't drop that out. R component, R component, R component, and the weight theta component. And of course there is no G. Okay, because we have absorbed it into the static pressure, so we are looking at dynamic pressure. So the R component momentum equation tells you that minus d theta square over r equals minus dp over dr. Now you should be able to start interpreting. What does it mean? What are the two terms? No, excellent. The one on the left hand side is the centrifugal force. So if there is a theta component of the velocity, then there will be a centrifugal force. In this case, V theta is also 0, so this will drop out. That means as you go in the radial direction, dp dr is 0. That means pressure is constant. In the radial direction, pressure is constant. That is, if I take a cross section like this, I traverse in the radial direction, there is no pressure variation. If I traverse in the angular direction, there is no pressure variation. Okay? The pressure variation is only in the axial direction because that's where the flow is. So the same thing for the theta equation, everything will be 0, not dp d theta. Okay, so that gives you 0 equals dp d theta, but you will have 1 over r. Remember, it has to be dimensionally consistent. So that's where the metric coefficient comes in to give you those terms, 1 over r dp d theta. Theta doesn't have any units, right? Just radians. So the first two equations then are trivial, in the sense that it simply says that the pressure doesn't change in those two directions. The dynamic pressure doesn't change in those two directions. let's call it step 2. This one? Yeah, this one, the physical interpretation for that term is if in your flow there is a rotation, theta, then there's a centrifugal force. And whenever there's a centrifugal force, that will create a pressure variation in the radial direction. Those two will balance, and there is an example of that coming up a little later. Okay? The second equation simply says when there is no Viscometer component, this is equal to 0. Okay? And that says that there is no variation in the R direction. There is no pressure variation in the R direction. There is no pressure variation in the theta direction. Okay? So the real equation that is non-zero, that is non-trivial, would be the axial flow equation, axial momentum equation, because that's where the flow direction is. That's where you have the pressure gradient. So it is steady, so you drop that. And look at the left-hand side, nonlinear term. Can you guys see that in the back? Do you have a printout? I don't know whether we can blow this up. These are scanned, so it may not even... Is it any better? So if you look at this, you have products of velocities. That's what makes it nonlinear. So it's Vr times Vz, V theta times Vz, the derivative of Vz, and Vz times derivative of Vz. But luckily for us, for rectilinear flows, Vr is 0, V theta is 0. And Vz is not 0, but dVz dz is 0, because it is fully developed. Exactly, very good. Okay, so this is not going to be 0, and in the theta direction there is no variation, and in the z direction there is no variation, but there is a variation of the velocity in the r direction. Okay, so this term will survive. We can throw this term out because we are neglecting, we are absorbing gravity into hydrostatic pressure variation. So the meaning of these pressure is whenever you drop G. So that equation then simplifies to minus 1 over rho dp dx. I guess I should call them as z. Is that an x or synonymous? Is the same as that? Is that x direction? Okay, so the second term is this term, but I've written it as an ordinary differential equation, ordinary derivative, because Vz is a function only of r. So that's how I simplify the Navier-Stokes equation for pipe flow analysis. Yeah.
Do you explain why you dropped rho G?
The reason I dropped rho G is because I'm dealing with dynamic pressure. So typically, this we did in the last class. I can write the pressure, total pressure, as dynamic pressure plus static pressure. And then when you have gradient of P, you can write this as gradient of PD plus gradient of PS. And gradient of PS plus rho G is equal to 0. Okay. And this sloppy use of terminology you will find in all the fluid mechanics books. You don't put PD, but when you don't see a G in it, you interpret P as dynamic pressure. Okay. Okay, so we have a second order ordinary differential equation in Vz, the axial velocity profile, and we need two boundary conditions. The boundary conditions come from physical understanding of the problem. So in this case, one of the boundary conditions is there is no slip condition at the wall. If you go to the pipe wall, the velocity is 0. Okay, so Vz at r equal to a, the pipe wall, the velocity is 0. The other condition is called a symmetry condition, meaning what would you expect the velocity to be at the center of the pipe? Maximum, right? Because of symmetry everywhere. So you if the velocity is maximum, its derivative must be 0, because the maxima and minima of the function is 0 as long as the function is continuous, right? So that's why we write the symmetry condition as at r equal to 0, at the center of the pipe, dVz dr is equal to 0. So these are the two conditions that we need to impose to evaluate the two integration constants that we will have. So the same trick as before. So write this as 1 over mu dp dx. The pressure gradient is known. You are imposing a pressure gradient from a pump to move this fluid. So that I'm going to call that as a known constant C. Okay, so that is a known constant, not an integration constant. That's known. So you separate and integrate once. Okay, and that is multiplied by R. So you get the R to the right hand side, and then move the dr. Okay, and then integrate both sides. Okay, and that is this step. So integral of derivative, so that simply gives you R times dvx dr. On the right hand side, integral of R dr becomes R square plus an integration constant A. Okay, and then you need to move this R one more time. Move this R to the right hand side. That's why you get A over R and then CR over 2, because R squared divided by R. So do an integration one more time. That gives you Vx equals CR square over 4 plus A ln of R, because you get dr over R. When you integrate dr over R, integral of that is ln R, plus another integration constant B. So in this one, A and B are unknown integration constants, but C is a known pressure gradient. Okay. Any questions on the integration steps? This you should be able to do. I hold you responsible for integrating simple ordinary differential equations like this in an exam. Okay. If the equation gets a bit more complicated, I'll give you a handout or something that will explain the steps to get the solution. Okay. So reducing the problem, analyzing the problem, understanding the problem is something that you should be able to do. If it is simple ODEs, you should be able to integrate, jump through that hoop. If it is complicated, I will help you through that, even in an exam. And once you get the result, you should be able to interpret the results. You should be able to compute quantities that we would be interested in. In this case, what is the flow rate? What is the pressure drop relationship? So in this case, put R equal to 0. Okay, actually in this expression, if you look at it, it becomes obvious. At R equal to 0, what is dvx dr? By symmetry, it is 0. That's one of the boundary conditions, right? At R equal to 0, the velocity gradient is 0. So what should A be? 0. Okay, so that boundary condition at the center allows you to determine what A is, and so A is 0 from symmetry. And then the remaining boundary condition you put in here. Okay, Vx equal to 0 at R equal to capital at A. At R equal to A, put Vx equal to 0. Okay, so this term would drop out for this boundary condition. Suppose, let me just throw a variation on you. I will keep doing this throughout the course, okay, and some of them may find themselves in an exam. I give you a very similar problem, but I say find me the velocity profile between two concentric cylinders. That is a double pipe heat exchanger. Okay, I want you to find the velocity profile in the annulus. What would change in the analysis that we have done so far? It's fully developed compared to this problem. The problem is the same. Let me state the problem. Okay, you have flow between two concentric pipes. I'm talking about flow in this region, outside the annulus. So think of the inside as a solid rod, and there is a pipe outside, and there is flow, one-dimensional flow, fully developed flow in the annulus area. Okay, so I apply a pressure gradient, and I want you to be able to predict the velocity profile. That's the only thing that will change. The velocity will be 0 at the inner wall. That will be one boundary condition, and the velocity is 0 at the outer wall. So this expression that you have here will remain exactly the same, because that is the function that satisfies the differential equation, that satisfies the Navier-Stokes equation, the momentum equation. So the velocity profile should have this functional form for that class of geometries, whether it is cylindrical pipe or an annulus, concentric annulus. Okay, then all that will change is the boundary condition will change. One of the boundary conditions will change. From symmetry condition at the center, because center doesn't even enter into the problem now, you should put a no-slip condition. When that happens, this term will not be 0. The logarithmic term will be non-zero. That we need to find out what A and B are, and then get the flow rate, etc. Okay, does everybody get that? Okay, suppose I ask you to solve that problem, another variation. Okay, suppose I ask you to solve that problem and then take the limit of that profile where the gap between the two cylinders becomes very small. Exactly. You should make that connection. Okay? So you should be able to take that velocity profile, and if I cut, now what I'm talking about is still a cylindrical annulus area, but the gap is so small. Okay? And if I have to predict what is the velocity variation across that gap, that should be the same as flow between parallel plates, the result that we already found out. Okay? So you should be able to mathematically take this limit and show that they are consistent in this limit of the gap becoming very, very small. Okay? So those connections are important, and these variations are the ones that I will be kind of checking on. Okay? But continuing on this problem, so you find out what the other boundary condition is by imposing this condition at r equal to a, b, x equal to 0. So you just solve for b and you get the velocity profile. Okay, I'm substituting back in terms of c for the pressure gradient. Okay. So what we get from this one is that the velocity profile in a circular pipe is parabolic. So if I plot the velocity profile, it's quadratic, you can see there. Okay, and it is, of course, assumption. It's a one-dimensional flow. And we also notice that the velocity profile is inversely related to the viscosity, square of the radius of the pipe. Okay, directly proportional to square of the radius of the pipe. Following on then, how do I get the flow rate? The same idea. Okay, now what I need to do is, it is Vx times dA. So I need to take an annular ring, a differential annular ring, okay, and that's going to be my dA. And at that radius, what is the velocity? That velocity is given by Vx. So on that ring, because there is no circumferential variation, the velocity is the same at any point on the circumference. I can simply take that as Vx times dA. What would dA be in this case? What is the area of a differential ring like that? 2 pi r. I guess you already have it there, right? But you should not just read from there, you should internalize it. You should do it in your mind, so that when you don't have that in front of you, you'll be able to write it still and continue on. Okay? So that area is 2 pi r dr. Okay, it's basically the circumference, 2 pi r, and dr is the thickness. So that is the area. Okay? So and substitute for the velocity profile itself, and then carry out the integration. So you have r square, r cubed dr, which becomes r to the power 4, over 4, and you already have a 4, that becomes 16. And then the second term, you have r dr, which becomes r square. Okay, r square over 2, which becomes 8. Between the limits of 0 to 8, from the center of the pipe to the outer radius of the pipe. When you substitute that, it simplifies to a square dp dx over 8 mu. I am, of course, dividing by the total area, pi r square, to get the relationship between the average velocity and the pressure drop, or you can write it as flow rate and pressure drop. That is a linear relationship. So that's a very nice result, because what it says is, if I plot, what do I want to plot? I want to plot, say, q and dp. I'm going to get a straight line. Okay, the question is, over what range of q will I get that to be a straight line? This is the question that we asked earlier. Will this relationship hold for any flow rate? The answer is no. When the Reynolds number becomes greater than 2100, this relationship goes like this, quadratically. It goes much faster. Okay? No, it should be the other way. You should correct me. That is, to pump additional amount of fluid, you need much larger pressure drop. Okay, so it is quadratic. The relationship is quadratic, but it is going this way. Okay, and the next question that one can answer is, what is the shear stress at the wall? Now, what you need to do is, which component of the shear stress am I interested in when I'm calculating the shear stress at the wall? So what is the wall? Wall is a circular pipe. So what is the normal to the wall? Is in the radial direction. So the first subscript in tau should be R, which identifies the surface. The second one should be the axis. So what is the force acting on the surface in the axial direction? Okay. Will there be a force acting in the circumferential direction? Not for this problem, because the flow is in the axial direction. Okay. And so it is that component, tau Rx. You just look it up in the appendix. And here you notice that there is no VR. There is no radial component, because that's the assumption that we made. Okay. So we have only dvx dr, and you know the velocity profile, so you can calculate that. You can calculate the velocity gradient from this expression. Take the derivative of this with respect to r and evaluate it at any plane that you want, any cylindrical surface that you want. So here it's at r equal to a. So that tells you that the shear stress at the wall is directly proportional to the pressure gradient. That is the force that you need to apply to the pipe to hold it in place when you are pumping a fluid. Okay, that's the force that the moving fluid will exert on that particular wall. Any questions? Yeah.
How you get that straight line? That Q over dp above.
Talking about this one?
Oh yeah, there is a graph straight line.
Oh, you're just plotting Q versus dp dx. Remember, C is 1 over mu dp dx, and then you have a to the power 4 pi over 8. Right? So if you want to ask you the question, what is the slope of that line, you can figure it out from here. 1 over mu, a to the power 4, etc. Right? So it's basically this relationship that we are plotting, which shows that it's a linear relationship between Q and delta P. Okay?
Yeah, and another question is, you talked about the variation, and you used to use the symmetry of r equal to 0, and you got the dv over dr equal to 0 plus t.
Right.
There is no velocity at the center.
Right, right. That's the case that I asked you to think about.
Still valid?
That's not that. Okay, that's a good question. I think this is what you mean. So here is an expression for the velocity profile. Okay, that is valid as long as this is a solution to this particular differential equation that we have here. Okay, that function satisfies that differential equation. Okay, now you can have many geometries that will have the same differential equation governing the flow. The two examples that we consider are one a completely empty pipe, the other one is an annulus, like this. Okay, so in this case, this differential equation will still satisfy the velocity profile, but the boundary conditions won't. So you have two constants A and B that you need to find out, right? So these have to be found out in such a way that the velocity at the inner surface is 0, the velocity at the outer surface is 0. So you don't even look at what happens inside because it's not in my domain. There is no flow in the center.
Yeah, but you list at r equal to 0.
Okay. I'm probably confusing you because I talked about this as a variation. Okay. The problem that I'm solving in the notes is basically the flow in a pipe without this annulus. For that case, this boundary condition is valid.
Well, in this case.
Which case? This case?
Yeah.
In this case, that boundary condition is not valid.
It's not valid.
It's not valid. So what I need to do is put 0 here and 0 here. Did I confuse all of you? It's an important part. I hope by talking about these variations, I'm not confusing you. Obviously, you gave me the answer and I said, okay, everybody understands that, and I move on. Okay? So, these variations are important. You think about them later on. Yeah, did you have a question?
So with that velocity velocity profile be fine for non-laminar flow?
No, that's a good question. That is not valid for non-laminar flow. The reason is for non-laminar flow, the assumption of V theta VR equal to 0 is not valid. You will have VR as non-zero, V theta as non-zero component. Experimentally, that's what we find. Okay, and if you ask a question, why does the flow become like that? When I am pumping it in only one direction, with a pump, with a flow in one direction, where is the mechanism for the flow to develop the VR component or the V theta component? Okay, that is turbulence. Turbulent flow has those characteristics. We observed that. Reynolds, who did this experiment in the 1800s, observed from experiments, even before these equations were derived, I think. And so he saw that the flow was streamlined laminar flow up to 2100, and above that it becomes turbulent. And to answer that question of where does it derive its source of fluctuations in the radial and angular direction, it took a long time. It still is not a fully answered, resolved question, but we understand where it occurs, and that is to do with stability. Okay. What do I mean by stability? Since we digress, maybe we should talk a little bit about it. A very common experience, I don't know how many of you are smokers, but if you're not a smoker, if you have incense or whatever, you light something, okay, an incense or a cigarette, and let the smoke evolve from there, and observe what happens to the smoke.
Okay. Laminar to one region,
It'll go as a laminar, as a very uniform steady stream, and then it just breaks up. Okay, that is what we would call a laminar to turbulent transition. Now, if you have a room that's completely stationary, there is no disturbance, there is no airflow, you can see this going all the way up to the ceiling. Okay, gradually diffusing out, but without this breaking up of the jet. Okay, so people now understand, and we can do analysis on these equations to predict when the transition will occur, when the flow will become unstable. But the slightest perturbations will cause the flow to become unstable. In process control, you know about stability all the time. How do you determine the stability of a differential equation? You look at the eigenvalues, you see whether it is positive. Growth implies it is unstable. Okay? The same ideas apply in fluid mechanics too. But we will come to that later on. So to answer your question, that equation does not apply when you go into turbulent flow. Okay? But it does apply for classes of laminar flows where the geometry would be variations on these. Okay, so it does apply for both pipe flow, which is completely filled with fluid, and concentric annulus as well. Now, once we get these velocity profiles, we saw that we can get the flow rate versus pressure drop relationship, and we can get the shear stress at the wall. Okay? Now, a very common expression that you would have seen in an undergraduate fluid mechanics course is you can express this as a friction factor. Friction factor Reynolds number chart, Moody chart, right? All of you have heard about that, right? You've used that. And in the laminar flow, you know that it is over 16 over Re. And that result pops out right out of this because the definition for friction factor is it's a shear stress divided by 1/2 rho V squared. That is a non-dimensional quantity that we define through that equation. You cannot ask why I defined that. You can define it in any other way you want. You will get a different number. Okay, but this is a standard definition that we accept. So it is shear stress divided by 1/2 rho V squared. V is the average velocity there. We already know the expression for the shear stress. We obtained it at the wall. Okay, and we already know what the velocities are, average velocities in terms of the pressure drop. We have it there. So if you combine it, for example, in the numerator, replace it by A dP dz, the pressure drop. In the denominator, I'm writing it as 1/2 rho V times V, but one of the V's I'm replacing it with the pressure gradient that I have here in this line. Okay, and so you'll find that the dP dz will cancel out, and you will get there is a 1/2 there. That's what cancels with this 1/2, if you're wondering what happened to that 1/2. And then you'll have A divided by rho V, A square over 8 mu. Okay, so that becomes 8 mu over rho VA. Now A is the radius of the pipe. So if you multiply on both sides by 2, then you get 2a is the diameter. That's how we define the Reynolds number. Reynolds number is diameter times velocity times rho divided by mu. That gives you your very famous 16 over RE result for laminar flow. Okay, which is valid only for Reynolds number less than 2100. But the surprising thing is that this result that we have for the velocity profile, flow rate, stresses, etc., does not have Reynolds number in it anywhere. Seems to be independent of Reynolds number. And that is the puzzle. So that means that it should be valid for all Reynolds number. If there is a Reynolds number in this expression, you can say, okay, it varies with Reynolds number in a certain way. But that expression that we have for the velocity profile, for the flow rate, are all independent of Reynolds number. Okay? So, and there is nothing in the development we have placed that it is not valid for high Reynolds number. So in principle, this velocity profile should be valid for all Reynolds number, no matter how large it is. In practice, as I said, it's the instability that causes it to lose its realizability, meaning you cannot realize it in an experiment. But people have done experiments recent years, in the last 10, 15 years or so, in extremely carefully controlled pipe flow. You have to make sure that the vibrations from the pump don't vibrate the pipe even by a micron. So very high precision control. Then you can achieve the Reynolds number, this velocity profile up to a Reynolds number of 100,000. People then measure the velocity profile at 100,000 to make sure that it agrees with this. Okay? It comes from external disturbances. If there are slightest disturbances externally, the unstable modes in the flow will grow, and then it will develop the VR component and big data component. But if the Reynolds number is low, those disturbances will be killed, because viscosity is a damping mechanism. So Reynolds number is a competition between inertial force and viscous force. If Reynolds number is high, inertia is high. When inertia is high, these velocities play havoc. They play their own game. But if the Reynolds number is small, viscosity is large. So any perturbation that you introduce will be damped out by viscosity. Okay, I think we should probably stop there. And
So if you have all the velocity, if the velocity component is only in the direction, then will there be a field of difference?
then there will be a
Like delta PD, dPd?
because these equations are all coupled, the
No, if there is only in theta direction, not in Z or R, so will there be a different difference?
yes, yeah. If it is pressure driven flow, there will be a pressure variation. But if it is a flow driven by a boundary, then there won't be. As in a rotating cylinder. For example, I have two cylinders, the inner cylinder rotates. Okay? Then you will not have. We are going to solve that problem in the next class, the rotating cylinder. Okay.